Let's take a look at this problem. We have the apparent power entering a certain load is 120 VA at a power factor of 0.866 lagging. If the RMS phasor voltage is 240 volts at 60 hertz, we have to determine these things here. Now, there are usually multiple ways of going about these problems, so you can always try it one way and then try it another way and see if you get the same answer, and you should. Alright, so to determine S going into the load, we know a number of different things. We know that if we look at the power factor, is P average over S. It also equals the cosine of the phase of the voltage minus the phase of the current, or that equals the cosine the phase of Z. So we can get we can say that 0.866 equals cosine phi Z, and if we take the inverse cosine of 0.86, we get 30 degrees. Now, we want to be careful here. This is important. Pay attention to this for your quiz. This says lagging. So when we have lagging, we want the positive value here, which is 30 degrees. If it had been leading, then you would say that it is negative 30 degrees. Because remember, the cosine of alpha equals the cosine of minus alpha. And so when you take the inverse cosine, it's like when you take the square root, and your answers can really be plus or minus. When you take the inverse cosine, your answers are really can be plus or minus. So which one you choose depends on whether you're leading or you're lagging. If you're leading, you choose the negative, and if you're lagging, you choose the positive. And then, so from this, we know, well, we have our angle, so we can say that our complex power equals the absolute value of our complex power, which we know, the magnitude, is 120. That's the apparent power. So the apparent power is 120. And so that would be 120 e to the j phi z, or 120 e to the j negative j 30. No, this is positive. This was if it had been leading, but it's not. It's lagging. To the positive j 30 degrees. And then if we wanted to have that as rectangular, that would be 103.92 plus J60. So that's A. We're going to come back in a minute and do it a different way and see that we get the same answer. Okay, now for B, to determine IRMS going into the load, notice that that is not just the magnitude. We also need to get the angle to go with it. We know that complex power, if we're using RMS, so complex power equals V RMS I conjugate RMS. And so I RMS conjugate equals S over V RMS, or I RMS equals S over V RMS conjugate. And so that would equal 120 angle 30 degrees over VRMS is 240 conjugate, and so that equals 0.5 angle 30 degrees conjugate, which is 0.5 angle negative 30 degrees. And so that is I RMS. Okay, well, let's say we had wanted to go about this a different way. And like I said, there's always lots of different ways to do this. So I could have said instead, if I wanted to, okay, just looking at the magnitudes, not looking at the angles, I can say that I RMS equals S over V RMS. And again, I'm not looking at the angles, just the magnitudes. And S was 120, and V is 240, and so that gets me 0.5. So I have that. And then I could say that phi is the inverse cosine of 0.866, which is 30 degrees, and then I keep it positive because it is lagging. And then I could say that S is S cosine phi. I say phi because that's what we say in Greek. Plus JS sine phi of z, or 240, and cosine, we already know that is 0.866 plus J, not 240, 120. J 120, sine of 30 degrees is 0.5. And then 120 times 0.866, 103.92 plus J60, and you can see that is the same as the S that I got up here when I wrote it in rectangular. And then from that, also, once I have the angle, then I know that phi z equals phi voltage minus phi current, and I know that phi z is 30 degrees, and the voltage is 0 degrees minus the phi of for the current, or the phi for the current, the angle for the current is minus 30 degrees. And so now that I know that, then I can write I RMS is the value that I found earlier, 0.5, angle negative 30 degrees. So just showing two different ways of doing it. Alright, now we need to find Z. And just like with all the others, there's going to be multiple ways of doing it. So I know that a number of different things, but in particular, I know that S equals Z times I RMS squared. And so Z will equal S over I RMS squared. These are the with the angles, and S we had was do we have a nice way of writing it? Yeah, 120 angle 30. 120 angle 30 degrees, and I was 0.5 angle minus 30 degrees squared. So that'll be 120 angle 30 degrees, and then to square the phasor, I would square the 0.5 to get 0.25, and then you multiply the negative 30 times 2, so it'd be minus 60 degrees. And then this is 120 divided by 1/4, which is the same as 120 times 4, which is 480. And when you divide phasors, you subtract. Oh, I forgot something here. This was supposed to be, this was not with the angle. This was supposed to be the absolute value, or the magnitude, just the magnitude, not with the angle. Sorry about that. So that's just 0.5 squared is 0.25, so that's just 480 angle 30 degrees. So this should have been S equals Z I RMS squared. 480 angle 30. Let me think if I have another way to do this. Don't see why not. Let's see. That's probably what I would have done on my own. I don't know why. I should always just do things my own way. So V equals I times Z, and $240 equals 0.5 angle negative 30 degrees times Z, or Z equals 240 over 0.5 angle negative 30 degrees, or that's 480 angle 30 degrees. Ohms. These are ohms. That was easier to do it that way. This should have been amps, and this is complex power, so that'd be VAR. No, just VA. Just VA. I was looking at the wrong problem. VAR is when you're looking at just the complex part. Okay, D. The equivalent resistance impedance of the load circuit should be of the form R plus J omega L, or Z equals R plus 1 over J omega C, which would be the same as saying J R plus J omega L, or R minus, or R plus minus J over omega C is the way we usually write that. Determine the value of L or C, whichever is applicable. So we had lagging here, and so that meant we had positive, so that means we have inductance. If you had negative, then you would have capacitance. So when you had negative, you would solve for this. We have positive, so we're going to solve for J omega L. So we'd say Z equals R plus J omega L. 480 angle 30 is 415.7 plus J240. And so this is the resistance. So that's the resistive part. And we know that J omega L equals J240, or omega L equals 240. Now it says that, if we go back and look at my problem, it says that we're at 60 hertz. Hertz is the frequency, not omega. So omega equals 2 pi times the frequency. So omega is 2 pi times 60, or omega is 120 pi. So 120 pi times L equals 240, or L equals 0.64, and this is inductor, so that would be 0.64 henries. So if you had, let's say instead you had one that was leading, so this is just if leading, and I'll just give you an example. Let's say that Z was, I'm just making this up, 40 minus J 50, and the frequency is 10 megahertz. Okay, so that means that omega is 2 pi times 10 times 10 to the 6, because mega is 10 to the 6. That big number, 6 6.3 times 10 to the 6.3 times 10 to the 7. So minus J50 equals minus J over omega C, or 50 equals 1 over omega C, or 50 equals 1 over 6.3 times 10 to the 7th times C. Or C equals 50 times 6.3 times 10 to the 7th. Wow, I can't believe I just made my Algebra 1 mistake. Yeah, so multiply both sides by C. Divide both sides by 50. See, I knew I should have been getting a very small number and not a very big number. 6.3 times 10 to the 7th times 1 over 50. And it would be whatever that is.